Hello and welcome to the 10th session of the Introductory Biostatistics Distance Learning course. Today's lecture is going to be about analysis of variance, which people often call ANOVA, the acronym for analysis of variance. So before we get started talking about analysis of variance, let's talk a little bit about what we've done previously. Remember that we had talked about confidence intervals, and then we talked about hypothesis testing, specifically the one sample and two sample t-tests. Okay, so hopefully where we've been with confidence intervals and one sample and two sample t-tests will help you understand the logical progression we're making to analysis of variance. Okay, so remember we had spoken about whenever you think about statistics, you should, or analyses that you want to do, you want to think in terms of the type of variable that you have as your outcome variable, and then also the type or types of variables that you have as your predictors or covariates or explanatory variables. All those words usually refer to the same thing. Okay, so when we have an analysis of variance type of setup, we're talking about a continuous outcome. Remember, so far we've only dealt with continuous outcome variables. Remember, t-tests and one sample and two sample t-tests both required continuous outcome variables: weight, blood pressure, some measure of a biomarker, and so on. These are continuous outcomes. But now, remember that a t-test had a continuous outcome as well, but it had a binary or dichotomous covariate. Remember, you were either in the treated group or you were in the placebo group. Now we're moving on to a categorical predictor, or categorical covariate. And by that we mean a covariate that has more than two levels, so three or more, okay? And we'll talk about how we can go about this, okay? So just to use the example that we were using from multiple sclerosis in the previous session, remember that there's this biomarker of interest. It's a continuous biomarker. And we wanted to investigate whether there was a difference in the expression of the biomarker for relapsing patients. So relapsing multiple sclerosis, or MS, versus progressive MS. Okay, so those were our two groups. And so we went through our 7 steps of hypothesis testing. First, we had to state the null hypothesis. Second, we had to state the type of data, and by that we mean the whole continuous outcome, binary, covariate, and so on. Third, we had to determine the appropriate statistical test. For this particular example here, it was a 2-sample t-test, right, because we had 2 groups. And then we had to state the summary statistics that we have and calculate a p-value. Those things would come from our statistical software package, and we're using Stata. Then, based on the p-value, we decide whether to reject or fail to reject the null hypothesis. And then finally, in step 7, we write our conclusion. Okay, and we went through several examples of those, and we use Stata to illustrate as well. Okay, so that's where we've been. Okay, so now let's talk about a few preliminary things before we move to analysis of variance, specifically type 1 error rates. So we spoke about type 1 error rates briefly before, but let's do it a little bit more now. So remember, when we get a p-value from our statistical software output, we then compare that to this 0.05. I just want to emphasize that there's nothing magical about 0.05. People have just decided to use this as a convention so that there's some standard that everyone is adhering to. There's nothing magical about 0.05. Remember, a p-value is a probability, and probabilities are continuous. So anytime you have a continuous measure and you choose a cutoff, the cutoff will be arbitrary. So 0.05 is arbitrary. If something comes out to be 0.51, it is not that different from something that's 0.49. So just keep that in mind. This is a continuous measure, and so when we have a cutoff, it's bound to be arbitrary. But just for the sake of having a standard, people have chosen this 0.05. Okay, so keep that in mind. With that said, the convention is that if the p-value is less than or equal to 0.05, we reject the null hypothesis. And if the p-value is greater than 0.05, we fail to reject. Okay. And so we use this 0.05 number because we've decided that that is the cutoff we're willing to accept for a type 1 error rate. So what is a type 1 error rate? Sometimes people call this alpha. So alpha, the type 1 error rate, is the probability that we reject the null given, remember that vertical line in probability notation means given. It's a conditional probability. That's something we learned in the third lecture, I believe. So the type 1 error rate, or alpha, is the probability that we reject the null given that the null is true. Okay, so if we reject the null when the null is true, that's an incorrect decision. That's why we call it an error, right? We've rejected the null, but it's actually true, so that's an error, and it's called a type 1 error because that's the worst kind of error that we can make, okay? And so people set this equal to 0.05, okay? And that's the type 1 error rate that we're willing to accept, okay? So just keep that in mind. That's a type 1 error rate. That's going to be important as we continue our discussion of ANOVA. Okay. All right, so looking at the big picture, remember in the last lecture we compared two groups with a continuous outcome, and we called that a two-sample t-test. Okay, so the logical extension is when we have more than two groups that we want to compare. So what are some examples? Well, we might have a trial with 3 or more treatment groups. Or we might have a basic science study comparing 4 different conditions. Okay, so anytime we have more than 2 groups, we can no longer obviously use a two-sample t-test, and that is when we move to ANOVA. And again, you want to always think about what type of outcome do I have, what type of explanatory variable do I have, and then use that to guide your decision on which type of analysis to use. Okay, so remember that's this table here. If I draw these lines, whoops. Okay, so you want to think about the type of outcome variable you have first, then the type of explanatory variable that you have, and then once you know those two things, you can know what type of analysis you need to conduct. Okay, so before we had a continuous outcome in orange and a dichotomous or binary explanatory variable, and so we then used a t-test. But now, in today's lecture, we still have a continuous outcome, but now we have a categorical explanatory variable. By that we mean 3 or more groups, and so therefore we're going to use ANOVA, or analysis of variance. Okay? So always think in these terms. What type of outcome variable do I have? What kind of explanatory variables do I have? And then once I know those two things, I'll know what type of analysis I need to conduct. Okay, let's make this all a bit more concrete with an example. So a recent study compared the hypointensity of gray matter structures on MRI in healthy controls. So healthy controls. We'll call those HC. In benign MS patients, benign MS, we'll call those BMS. Secondary progressive MS patients, I'll just write secondary progressive MS, so we'll call the SPMS, and primary progressive, primary progressive MS. So primary progressive MS. Okay, so this hypointensity is our outcome. It's a marker of disease and it's a continuous variable. And our question is there any difference among the different groups, these 4 groups that we've listed here, in terms of their hypointensity, the continuous outcome of interest? Okay, so we're going to conduct a hypothesis test, right? So we'll just go through those same steps as we did before. So starting with writing out our null hypothesis. Okay, so the null hypothesis assumes that there is no difference between the groups in mean hypointensity. So let's write that out. Remember, we write our null hypothesis in this way. And remember, our hypotheses always concern the population parameters of interest. And we denote population parameters typically with Greek letters, okay? So we're interested in the population mean, so that's mu, in the healthy controls. And in the null hypothesis, the mean in the healthy controls is equal to the mean in the benign MS patients, equal to the mean in the secondary progressive MS is equal to the mean in the primary progressive MS patients. Okay? And again, we have a continuous outcome, which is this measure of hypointensity, and a categorical predictor. Namely, which group are you in? Are you in the healthy control group? Are you in the benign group? Are you in the secondary progressive, or are you in the primary progressive? Now, what would the alternative hypothesis be? Remember that between the null hypothesis and the alternative hypothesis, we have to cover all possibilities, right? So you might be tempted to say that the alternative hypothesis is that the mean in the healthy controls is not equal to the mean in the benign, is not equal to the mean in the secondary progressive, is not equal to the mean in the primary progressive. But this is wrong, okay? This is a common mistake, so don't make this mistake. Why is this wrong? Because if this were the alternative hypothesis, between these two things, we wouldn't cover all possibilities. And why is that the case? We could have a case where the mean in the healthy controls is equal to the mean in the benign MS, but they're different from the other two groups, right? This alternative hypothesis that we wrote here is saying that all the means are different, okay? So in fact, the real alternative hypothesis, if I can just erase this stuff here, the real alternative hypothesis, remember, it has to cover all other possibilities not covered by the null that we stated, okay? So the real alternative hypothesis here is that at least one of the means is different. So hopefully you see how this alternative hypothesis When combined with the null that we have here, the null here says that all of the means are equal. The alternative here says that at least one of them is different. And so between those two, those things cover all possibilities. Okay? So hopefully that makes sense. Don't fall into the easy trap of saying that the alternative hypothesis is that they're all not equal. Instead, it's that at least one of them is different. Okay? So how could we investigate this hypothesis? Well, you might say, given the tools that we already have, why don't we just complete all pairwise comparisons? So what would that look like? Whoops, that didn't turn out how I wanted. Okay, sorry about that. I'll just write it out. So remember we had 4 groups, so we could do a bunch of null hypotheses using pairwise t-tests. We could say the mean in the healthy controls is equal to the mean in the benign MS. That would be one 2-sample t-test. Then we could conduct another 2-sample t-test where the mean in the healthy controls is equal to the mean in the secondary progressive MS. And then a third 2-sample t-test. The mean in the healthy controls is equal to the mean in the primary progressive MS. And then a fourth 2-sample t-test. The mean in the benign MS is equal to the mean in the secondary progressive MS. And then a fifth null hypothesis 2-sample t-test. The mean in the benign MS is equal to the mean in the primary progressive MS. Right? And then a last one, our 6th null hypothesis, that the mean in the secondary progressive MS is equal to the mean in the primary progressive MS. Okay? So we would have 6 pairwise 2-sample t-tests to conduct. Okay? So you might say, hey, I already know how to solve this problem of comparing these 4 groups. I can just conduct this whole bunch of 6 2-sample t-tests. Okay, so what happens when we do many tests instead of just one? Well, this is where we get back to the type 1 error rate that we spoke about. The reason we don't do these 6 different pairwise tests is because we encounter problems with the type 1 error rate. Remember again, we said the type 1 error rate, or alpha, is equal to the probability that we reject the null, given that the null is true. Okay? So it's an incorrect decision, it's an error. We've rejected the null when it's actually true. Okay? So if that's alpha, if that probability is equal to alpha, remember alpha is just a number, we usually set it equal to 0.05, so don't get confused by that. This alpha is usually just equal to 0.05. I can flip this around and say, if I keep the conditioning part the same, namely that the null is true, and I just change my decision to fail to reject the null. Remember, these two things have to add up to 1. So this is just going to be equal to 1 minus alpha. Okay? So hopefully you see how that works. Remember, they're both conditioning on the same thing, namely that the null is true. So when the null is true, we have 2 decisions. We can either reject or we fail to reject. And so between those 2 probabilities, they have to sum to 1. So you see 1 minus alpha plus alpha is just equal to 1. So that's how I knew this part was equal to 1 minus alpha. Okay? So we're going to use this going forward. Okay, so what about in this example that we're talking about? So in this example, alpha is equal to the probability that we reject the null given, whoops, these ones look like givens, so let me make them look like ones. Alpha is equal to the probability that we reject the null given that the null is true. So in this example that we were talking about, when is the null true? The null is true when the mean in the healthy controls is equal to the mean in the benign MS, is equal to the mean in the secondary progressive MS, is equal to the mean in the primary progressive MS. Okay? So if we had completed the 6 pairwise tests that we spoke about, what is the chance that we would reject the null that all the means are the same? Okay? And so to answer this question, so let me back up so you don't get lost in the details. What we're trying to do here is show why we don't conduct those 6 pairwise tests that we laid out. Okay? So the problem comes with the type 1 error rate. So right now, this is all just a justification for not conducting 6 pairwise t-tests, but instead for using ANOVA, which is the topic for today. Okay, so hopefully the big picture makes sense. Right now, we're just in the justification for why we're proceeding in the way that we are. Okay? All right, good. So, there are 2 types of error rates. 2 error rates. First, there's the component-wise error rate. Okay, so that's the type 1 error rate for each comparison. The type 1 error rate for each comparison. Okay? And then, second, so that's for comparing group 1 to group 2 only, or group 2 to group 3 only, and so on. Then, there's the family-wise error rate. Okay? So that's the type 1 error rate for the entire group of comparisons. Okay? So remember, we had said that if we were going to compare these 4 groups using only 2 sample t-tests, we would have 6 tests to conduct. Okay? So keep this issue in mind, the issue of component versus family-wise error rates. Okay? So how do we compute the family-wise alpha level? The family-wise alpha level. Okay? So to calculate for our 4 group comparisons, we consider that we would reject the null if any of the t-tests showed a significant difference, okay? So this would look something like this. So the alpha would be the probability that we reject at least one t-test given that the null is true. Okay, this is the family-wise error. Hopefully you can see why this is the family-wise error, right? Because here we said at least one. So we could have made, out of our 6 tests, we could have made 5 correct decisions, but only 1 incorrect decision. and even if that happened, we would be in this scenario of this alpha, because we rejected at least one t-test that was true. Okay? So how do we calculate this? Okay? So we'll do it in the same way that we did before. We'll just say that this thing is equal to 1 minus the probability that we fail to reject all tests, all t-tests, given that the null is true. Okay? Which is equal to 1 minus the probability that we fail to reject one t-test given that the null is true. Sorry. And then this is, so this is a big here, and this is to the 6th power, because we have 6 tests to conduct, right? So hopefully that makes sense. 1 minus this big probability to the 6th power, okay? So now, what does that look like? That is equal to 1 minus 0.95 to the 6th, which is equal to 1 minus point, let me just erase a little bit here. 1 minus 0.735, which is equal to, whoops, which is equal to 0.2, sorry, this is getting a little full, but is equal to 0.265, okay? So now this is our family-wise error rate, okay? So remember at the beginning we said the error rate, the type 1 error rate that we're willing to accept is 0.05, nothing more than that. Then we said we have these 4 groups to compare, and in order to compare them, we have to conduct 6 different tests. And if we conduct these 6 different tests, it turns out that the family-wise error rate through this calculation that we've shown is equal to 0.265, which is now much, much bigger than 0.05. Okay? It's inflated well above 0.05. So this is not something that we want. We don't want our error rate to be so large. We don't want to make type 1 error rates because those are bad conclusions. Right? That's like when we conclude that a treatment really works when in fact it doesn't. It's no different than a placebo. Okay? So that's a poor decision to make, and it's something we want to avoid in all situations, particularly in medical research. Okay? So you can see by doing these 6 pairwise t-tests, we now have this very inflated family-wise error rate. So that's something that we want to avoid. So how can we do that? Well, we have, what can we do? We can do 2 things. We can adjust the alpha level. Remember, we had started with the alpha level of 0.05. We can adjust the alpha level for each comparison so that the family-wise error rate stays at 0.05 instead of getting huge at 0.265 like we have in this particular example, or we can use ANOVA, which is the topic of this lecture. Okay, so let's proceed with ANOVA. Okay. So ANOVA. Analysis of variance. So what's the null hypothesis again? It's that the mean in the first group is equal to the mean in the second group is equal to ... We can have as many groups as we want, is equal to the mean in the nth group. Okay? This is just, whoops. This is just a way of saying n can be any number. That's an n. So in our example, there were 4 groups, but it can be any number that we want. So we're testing whether the mean is equal across groups. And I want to write that down just so you don't get confused. Testing whether the mean is equal across groups. So what's interesting here is that our null hypothesis, again, is about the means, right? Mu is means. And we're testing whether the means are equal across groups, right? But then we called this thing the analysis of variance, right? So you might get confused and say, hey, I thought we were talking about means, but you said this thing is called the analysis of variance. What's up with that? Well, it turns out to be able to conduct a hypothesis test about the means, we have to use the variances, okay? So don't worry if that doesn't make sense now. It's what we're going to explain in the rest of the lecture. But it's something that's very interesting and something cool to keep in mind. To compare the means, we assess the variances, okay? And again, we said that the alternative hypothesis is that at least one mean is different. Okay? Okay, so again, thinking about the types of variables that we have a continuous outcome. Remember that, that table that we showed, a continuous outcome and a categorical predictor, okay? And remember, whenever we conduct any sort of statistical test, there are going to be underlying assumptions that that test has. Okay, so what are the assumptions of ANOVA? So the assumptions for ANOVA are that the underlying distributions of the population are normal, and that the variance of each group is equal. Okay, remember in our example we had 4 groups, so in order to conduct ANOVA, we would assume that the variance in these 4 different groups is equal. So this is called, it has a funny name, homoscedasticity. So you can impress your friends and family by telling them that you know about homoscedasticity, okay? So homo means same, scedasticity refers to variance, so that's just another way of saying that the variance of each group is equal, homoscedasticity, okay? So these assumptions hopefully look very, very familiar to you because they're very similar to the assumptions that we had for the 2-sample t-test. We had underlying normality, and before we just had that the variance of the 2 groups was equal, though we were able to relax the equal variances assumption in the 2-sample t-test case as we saw in Stata. Okay? All right. So, what does this look like in a picture? Usually we can understand things a lot better when we look at pictures. Okay? So here you can see a bunch of overlaid normal distributions, right? So here are the normal, here's the outer, the outermost one is here, the innermost normal distribution is here, and these vertical lines here represent their means. You can see these 4 different vertical lines. So you can see that the means in these 4 different groups are very, very close, okay? So that's how it would look in a picture where the 4 different groups were all very similar. How about a picture where the 4 different groups are not similar? What would that look like? That would look something like this, right? So here's the mean of one normal distribution, here's another mean, the third mean, and the fourth mean. And so you can see in this picture, as opposed to the previous one, there's a lot of variability in between groups, okay? So the variability between groups, here's one variability, variability between another groups, variability with other groups, and so on. The variability between groups is much smaller than the variability within a group. And now you're hopefully starting to get a sense for why, in order to compare means here, 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 and here, we look at variability. We look at the variability between groups and see how that relates to the variability within groups, okay? So now hopefully you're getting a sense of why we call this thing analysis of variance, to compare means. Okay, so let me just write that out to emphasize the point. So we were looking at sources of variance. Okay, there are going to be two sources. There's going to be the within group variability, okay? And that is to say, when we sample from a group, for example, when we sample from the healthy controls, there's going to be variability from person to person in that group. Not all healthy controls are going to have the exact same outcome measure. There's going to be some variability. We refer to that as within group variability. And then, of course, there's between group variability. And that refers to the difference from group to group. So, you know, someone in the healthy control group versus someone in the benign MS group, okay? So if the between group variability is large, then that means that the means of the two groups, or of the several groups rather, is likely not the same. Okay? So let's take a look at this picture again, just to really drive home the point. Okay? So we can use the two types of variability to determine if the means are likely different. Okay? So let's look at, so within group variability would be here, right? Whereas between group variability in this particular example, these vertical lines represent the means. So you can see here that the within group variability, this stuff, is much larger than the between group variability here. Okay? So in this particular example, that we would probably conclude that there's no difference between groups. Okay? But in the other example, let's take a look at that picture again. The variability within a group, the variability within a group is much smaller than the variability between the groups. Okay? So here the between group variability is much greater than the within group variability, and we would likely reject the null. Remember that the null is that mean 1 equals mean 2 equals mean 3 equals mean 4. So in this case, we would probably reject the null in favor of the alternative, and we would conclude that at least one of the means is different. Okay, so now I'm going to get into a bit of mathematical notation. I just want to make sure that you don't get too confused or intimidated by the mathematical notation. The point of the math is to provide you with some insight as to what's going on. You don't have to memorize any of the formulas. You don't have to be too worried about it if you're not understanding it, because all of these calculations are going to be carried out by the statistical software. The point of the mathematical notation is to provide you with some insight into what's going on in the background when you run ANOVA in Stata or in your favorite statistical software package. Okay, so again, don't get intimidated by the mathematical notation. Don't worry too much if it doesn't make sense to you. The whole point of it is to provide a bit of insight into what's going on. Okay, so let me display some of that here. Okay, so first you see we have this thing xij. What does that refer to? That is a single observation from a patient, from patient I. From patient I, what do I mean by patient I? I is a number, so from patient 1, from patient 2, from patient 10. So this is the observation from patient I in group J. Okay? So if I were to write, say for example, x1, 15, that would be the observation from the first patient in group 15. That would be a lot of groups, right? So we probably wouldn't have something like that. Instead, we would have something like x15, comma 1. So that would be the 15th patient in the first group, okay? Similarly, if I wrote x3, comma 2, that would be the third patient in the second group. Okay, that's xij. So that's the actual outcome on a single specific patient. Okay, so hopefully that notation makes sense. Just a last example, maybe I'd have x7, 3. That would be the outcome for the 7th patient in the third group. Okay, remember in our example we had 4 groups, so we could have something like x64, the 6th patient in the 4th group. Okay, so that's the first step. xij is the observation from patient I in group J. Okay. Next, we have x bar sub j. Okay, and what is this? This is the mean of group J. Remember now we have several groups. In our example we had 4 groups, and so we would have x bar sub 1, that would be the mean in the healthy controls. We would have x bar sub 2, the mean in the benign MS patients, x bar sub 3, the mean in the secondary progressive MS patients, and x bar sub 4, the mean in the primary progressive MS patients. Okay? So remember now, this part is an individual's actual observation. This is the mean for the jth group, and this, x with 2 bars, x double bar, is the grand mean over all groups. Okay? Great. Okay, so hopefully the notation makes sense. So here, remember, we had 4 groups: the healthy controls, the benign MS, the secondary progressive, and the primary progressive. And then if we combine them all, we get this x bar bar. Okay, and this mathematical notation here just means take all of the observations in that group, add them all up, divide by the number that there are. And this means take all the means, add them all up, divide by the number that there are. Okay? So don't get intimidated by the notation. It's very simple. All it's saying is just add them all up and divide by the number that there are, just how you would anytime you're calculating a mean or an average, okay? So again, 3 things here: an individual patient's outcome, the outcome for a particular group, and then the outcome for overall, the mean overall outcome. Okay. Okay, so remember now we're talking about sources of variability, which is what we're using in ANOVA. Okay? So let me put up another equation. Again, don't be intimidated by the equations. Don't be too worried if it doesn't make sense to you. It's just here to try to provide you with some insight. Okay? So what am I looking at here? Here is xij minus x bar bar, right? So based on what we learned on the previous slide, this is the distance of each observation. Remember, xij is the ith person in the jth group's observation. The distance of each observation from the grand mean. This is the grand mean. So we have that, right? Each individual's distance from the grand mean, and we can take that, and break that down into groups. Okay? So what am I going to do? Just a bunch of, I'm just going to go through a series of mathematical manipulations, right? So we have xij minus x bar bar, and now I can say that that is equal to xij minus x bar bar, I haven't done anything yet, plus x bar j, remember that's the mean in the jth group, minus x bar j. So all I did was add and subtract the same number, which means I didn't do anything, right? If I add 5 and subtract 5, you didn't do anything. So I added x bar j and I subtracted x bar j. And now, if I just group these things together, if I just rearrange the groupings and say, here's the distance between the actual ith person in the jth group, their observation, from the mean in the jth group. Well, what do we call that? That is called the within group variability. Right? Because this is within a group. All the people here are in the jth group. This is the ith person in the jth group minus the mean in the jth group. And then this part is the between group variability. And why is that? Because it is the distance from the mean of the jth group from the grand mean. So that's the between group variability. So you see how I did that? I just started with the distance of each observation from the grand mean here, and then I broke it down with just some simple mathematical manipulations to the within group variability and the between group variability, this concept that is driving analysis of variance. Okay? And remember, just like when we looked at the standard deviation or the variance, we don't just look at differences, but we look at squared differences, right? So what would the squared differences in this case look like? Whoops, that's not the one I wanted. Whoops, that was the one I wanted. I apologize. Okay. Okay, so this part is the total sum of squares which is sometimes denoted as SST, the sum of squares total. This part is the within group sum of squares, within group I'm going to just say sum of squares. This is sometimes called SSW, right? It's within group because it's looking at the difference from a single person in the jth group to the mean in the jth group. And then this part is the between group sum of squares, and that we write SSB. Okay? So as we discussed earlier, we're going to compare the two sums of squares to determine if the group means are equal. We're going to compare the within group sum of squares to the between group sum of squares. Okay? So again, all these formulas, don't get intimidated. They're just to give you some insight. This whole concept of ANOVA revolves around the comparison of between group variability to within group variability. Okay? Okay, so just a few more of these equations. So the within group variability, remember that is the sum of squares within, can be further broken down in terms of individual group standard deviations, right? So here I'm just summing over people, that's the I. Here I'm summing over groups, that's the J. And I can break that down into just one sum over groups using the individual group standard deviations S squared sub J. Again, don't worry about the particulars of this formula. Absolutely don't think about memorizing it because it's not important. It's just to give you some insight. Okay. So the result is called the within group mean squared error. So let me pull up the formula for that. Okay, so this MSW is the mean square error with, and then it's the within group. Okay. Okay, so we've taken these individual group standard deviations, the standard deviations for the first group, standard deviation for the second group, standard deviation for the kth group, divided by the total sample size, n1 plus n2 plus nk, minus the number of groups. There are k groups total, so we subtract the number of groups that there are. Okay, and this gives us the mean square error. Again, don't worry if this looks confusing. It's just get the general idea. Okay. Now we can do the same exact thing for the between group variability. Okay. So this is the sum over individuals. This is the sum over groups. I can just make it a sum over groups in this fashion. And then I can look at the equivalent. This is called the mean square error between groups. Okay? Sorry, I don't know why this should be an n minus 1, the number of groups minus 1, okay? Or rather, k. Okay? And this should be k as well. Okay. So basically all we're getting at is how to break these things down, the within group, the between group, and so on. Okay? Now that we have the between group and the within group pieces, we can construct our statistic. right? Remember, that's how we get to our p-value, by constructing this statistic. And in the ANOVA case, the statistic is called an F-statistic, okay? And so what we do is we take the between group mean square, divide by the within group mean square, and we showed in this calculation how to get that. That gives us the F-statistic, okay? And the F-statistic now has two parameters, as you can see. Okay, they're degrees of freedom. The F-statistic has k minus 1 and n minus k degrees of freedom. Remember, k is the number of groups. Okay, in our example, we had 4 different groups: the healthy controls, the benign MS, the secondary progressive MS, and the primary progressive MS. So k would be 4. And n is the total sample size. Okay, good. So you can see we have an F distribution with k minus 1 and n minus k degrees of freedom. K is the number of groups, n is the total sample size. Okay? All right. And so that gives us, based on all the things that we've looked at, we can now construct an ANOVA table. Okay? So lots of statistical software will show you ANOVA tables. So let's see what that looks like. An example of an ANOVA table. Okay, here's an example. It's easier to see if we just add these lines. Okay, so we have our sources of variation. Well, there's between, there's within, and then there's total. Okay, and then the SS is the sum of squares, the degrees of freedom, the mean square, the F value, and then the P value. Okay? So you'll sometimes see this in kind of introductory stat textbooks or in your statistical software, the ANOVA table. And we discussed a bit about all the components of this. The sum of squares here, between, the sum of squares within, the sum of squares total. Remember, when you're looking between groups, you have k groups total, so k minus 1 degrees of freedom. Looking within groups, you have n minus k. Add those things up. You have n minus 1 degrees of freedom, the mean squared between, the mean squared within. Then we take the ratio to get the F statistic. Then we compare to an F distribution to get our p-value. So let's look at the example for the example that we've been the ANOVA table for the example that we've been working with looks something like this. Okay, remember we had the 4 different groups: healthy, benign, secondary progressive, and primary progressive. And this is, here are the means in the 4 different groups, the corresponding standard deviations, and the sample sizes in each of the 4 groups. Okay, remember we said in the first lecture, and hopefully we'll repeat throughout the course, a very good first step whenever you conduct any sort of statistical analysis is going to be to look at plots. So what does a plot of this look like? Remember, the outcome is this measure of hypointensity. It's a continuous outcome. Here it is in the benign, in the healthy controls, the primary progressive, and the secondary progressive. Okay? So this plot is very helpful in letting us know whether the means look similar. It looks to me like they might be a little bit different, right? This one, the healthy controls seem to have a higher number than the rest, and there seems to be less variability in that group. Okay. Okay, so let's actually conduct our hypothesis test, because just by looking at the plot I might guess what the outcome is going to be, but I need to be rigorous and actually conduct the statistical test to come to my conclusion. Okay, so remember we're going to go through our 7 steps of hypothesis testing. First step, what is the null? I'm just going to say that the mean in these 4 groups is equal. And the alternative is that at least one mean is different from the rest. Okay. Step 2, I have to say the type of data that I'm working with. Well, I have a continuous outcome and a categorical predictor or covariate. What kind of analysis am I going to conduct? ANOVA. Then I use statistical software package to give me my test statistic. And we said that when we're conducting ANOVA, it's an F-statistic. And in this particular example, it's equal to 5.04. We'll show that with Stata. The corresponding p-value for that F-statistic is 0.0027. Then we compare 0.0027 to 0.05. Turns out 0.0027 is less than 0.05, so we reject the null. Okay, and then finally in the last step, our conclusion, we conclude that the mean hypo is different in at least one group. Okay, so hopefully you don't feel satisfied by this conclusion. Our conclusion is that the mean hypo is different in at least one group. And so any sort of investigator would say, well, in which group is it different, right? That would be the next step. So we're going to get to that, so don't worry. But this is the conclusion that ANOVA allows us to reach, that the mean hypo is different in at least one group, okay? And so to just show you the ANOVA table, what the ANOVA table looks like for this example, here it is. Here's our p-value that we said was less than 0.05, which is why we rejected. Okay, and how would we do this in Stata? We can use this command called one-way, because this is a one-way analysis of variance. Then it gives us the mean in the 4 groups here, the standard deviations in the 4 groups. The frequency means the sample size in each group. Here's the corresponding p-value. Okay, and you'll notice Stata actually gives us a test for equal variances as well, which has a corresponding p-value. We'll work through an example of this in the corresponding Stata tutorial for ANOVA. There's also an alternative command here. Remember, we used one-way. There's a more general command, which is called ANOVA. ANOVA. So you see, you type in ANOVA, which is the command that you want, then the outcome variable, hypo, then the predictor, which is the group that you're in. And here's our, and it gives us our ANOVA table, and here's our p-value, 0.0027. Okay? Okay, so a few notes before we wrap this section up. Remember the assumptions that we're making. One assumption is that of equal variances, right, between the groups, and that of normality, underlying normality in the populations. But ANOVA is quite robust to departures from these assumptions. What does that mean? If these assumptions don't hold, ANOVA is usually still valid, but we'll talk more about this later. Okay? Now, the key step, the most important step here is that we got a p-value less than 0.05. We rejected our null. We concluded that at least one of the means was different, but we don't know which mean is different, okay? So we're not done yet. So in other words, ANOVA is often considered a first step, okay? So we wouldn't just stop here. We wouldn't write a paper for the medical literature and say, the means in these 4 different groups are not equal, because no one would be satisfied with that. They would instead want to know, how do they differ? Which group has a higher mean? Which group has a lower mean? And so on. So ANOVA is often considered a first step, okay? So if we reject the null hypothesis in our ANOVA model, which we have done here, so if we reject, as we did in our example, we then move to pairwise comparisons. What do I mean by that? Well, we concluded that at least one group was different. So now I'm going to move to pairwise comparisons, which means I'm going to compare the healthy controls to the benign MS, to the secondary progressive MS, to the primary progressive MS. Okay? Which is very similar to what we said at first, where we were going to conduct those 6 different pairwise t-tests, but we ran into that problem of the family-wise error rate. So in the next session, I'm just going to stop here. We are going to focus on the next step, which is to conduct these pairwise comparisons. I apologize for going over the 45 minutes, but ANOVA is a complicated analysis, so it's good to kind of get into depth. So just remember that we're looking at, we're comparing the between group variability to the within group variability, reaching a conclusion, and then if that conclusion is that at least one of the groups is different, we then move to pairwise comparisons, which is what we'll talk about in the next session. Okay, so I will see you then.